Welcome everyone to the second guest lecture in our series. Hanjun Dai is a staff research scientist and research manager at Google DeepMind. He obtained his PhD from Georgia Institute of Technology with La Song. His research focuses on efficient generative modeling for text, image, and structured data, and the corresponding fundamental algorithms in sampling and optimization. He has won many accolades, both within Google and in the broader machine learning research community. And on a personal note, so a close collaborator and one of the most knowledgeable AI researchers I've had the pleasure of working with. So with that, I'll hand it over to Hanjun.
Thank you so much, Mayor, for the introduction. And also thanks a lot for inviting me to give this lecture. And as Mayor mentioned, we have been long-time collaborator for quite several years. And yeah, we always enjoy working with Mayor, and really my honor to be here to talk about the language model and the reinforcement learning in general. Is my volume okay? I assume it's okay, so I'll just proceed. Yeah, so today, sorry. Okay. Yeah, so today I'm going to talk about some basics and also latest advances in the preference optimization for the large language model. Maybe one of the most famous algorithm in this field is the reinforcement learning from human feedback, but I will cover quite some portion of it, and meanwhile also cover other types of algorithms that can also do this kind of preference optimization. And that's where this title come, and um, let's jump into the class. So now we all know that these great language models are trained by this like after the pre-training, the reinforced learning from human feedback is a critical step to make this language model great. And especially the very recent O1 from OpenAI, they claim that this deep, long reasoning ability is trained using the reinforcement learning, and the language model is able to automatically come up with this high quality and precise intermediate reasoning steps that can help generate the good answer, not only for this toy example, but also for more realistic coding and other examples. But just a couple of years before this, probably some of you already know that, for example, OpenAI, they train the Dota 2 agent, and they can compete with the top teams in the world. And also for DeepMind, they use the same, like similar technique, like reinforcement, but definitely many others, to achieve like expert level of StarCraft 2. And these are all impressive results. And I wouldn't say this is the very beginning, but this is roughly the time where people realize that with the reinforced learning, we can achieve human level performance in many tasks. And I think this is a very classic paper in 2015. It's called the DQM, and it's not too long ago. And this paper teaches the computer to play this game, and it only has limited action space, and but it uses the visual input, and it can be general. This technique can be general to generalize to many games in this Atari bundle. So as we can see, that the reinforced learning has been the key for many recent breakthroughs. And I want to quote the beta lesson from Rich Sutton. In his website, he comment that one thing that should be learned from the beta lesson uh, is the great power of general purpose method, of methods that continue to scale with increased computation, even as the available computation becomes very great. So the so-called beta lessons, in the past, people have been spending quite some time to put human intelligence into the system. For example, like inventing expert system, all kinds of rule-based system, and later on, they were replaced by some learning methods, but still in with human priors. For example, like hidden Markov models for speech recognition, for example, they're great, but if we have more compute and more data, they wouldn't scale as good as more general purpose methods. That's so-called the beta lesson. It seems like we somehow need to spend less time on thinking about the sorry, any yeah, if we maybe we should spend less time on thinking about putting the human intelligence, but thinking more about how to leverage more power of compute and data and other resource. So the conclusion in the beta lesson is the so-called the two methods that seems to scale arbitrarily in this way are search and learning. And I think reinforcement learning is a term that is a combination of search and learning, where the agent itself needs to actively search and learn from its own trajectory. And I think that's why maybe we can see that the reinforcement learning has been the key for the many success in the past decade. Okay, so I will start from some RL basics, and but feel free to interrupt me if I'm going too slow or too fast in any part. The purpose is to establish some common framework, especially from the distribution matching perspective, and we'll later see that this perspective can be used to derive many algorithms in the literature, and especially the recent literature. Yeah, so we start with this KR divergence. Probably many of you are already familiar with this. Suppose in the language model learning case, the two distributions we are going to match are one, the P, let's denote it as the distribution of the human generated language. But it's up to you to define what type of human you want to fit. Maybe let's fit the average human, that's the majority population, or maybe we only fit those genius or experts, which may be just a minor portion of the entire population, but maybe they are great, so that's why we only want to align with them. So it's up to you to define the target you want to fit. And the Q is the distribution of a language model, and that's the distribution you want to learn and try to align with the P. So let's just recap the KR divergence. It is written in this form, and when it achieves zero only if the two distributions are identical. And most importantly, this KR is asymmetric, which means the KR of P versus Q is different from KR of Q versus P in most cases. So let's just expand the term a little bit. Basically, here we just split the log of ratio into two terms, and I will notice that in this case, the first term has nothing to do with Q, so we can simply throw it away. And what we have in the end is just the second term, which is the term that we should be all familiar with. It's called the maximum likelihood learning, or this cross entropy. So in this case, we collect the data from the P, the human distribution, and do the so-called teacher forcing, or SFT, the supervised fine tuning. that you're probably already familiar with. So that's the how we connect this supervised learning to the distribution matching from the direction of P to the Q. But how about we do the distribution matching from the other direction, saying that we swap the position of P and Q, and that will be the type of reinforcement learning we are going to talk about today. Yeah, so basically, this is called a reverse KR, where the target you're optimizing is on the left side of this notation, and for the reverse KR, definitely it is not as easy as the forward KR, where this term is a bit involved. So, but you can see that I don't know if you can see my cursor, but let me see if can you see my cursor? If anyone can speak up.
Yes.
Okay. Okay, thanks. Yeah, so in this case, we can see that for the given sample X, and this X under P, basically indicates how likely it is for an X squared P to generate X. So roughly you can see that if we want to maximize this thing, so we want to maximize the X such that where the probability of X such that it achieves the highest reward. But at the same time, you definitely want to balance this term, the second term, this denominator indicates this the entropy of the distribution itself. So making sure you don't collapse. So if we rewrite this into some more generic form, that's the type of the very classical reinforcement learning that we are going to deal with. Basically, learn the distribution of say, the policy that generates X, such that you want to maximize the expected reward in this way. And to derive the way that we can optimize this, let's take the gradient with respect to Q of this objective. And by leveraging some property of this equation, we can, for example, for the first equation, we can swap the summation, the gradient. And then the second term is just adding dummy terms of QS divided by QX, so you can easily cancel that out. But if we put the ratio together, then we can get this gradient of log Q. So and then we write a little bit. That's basically the policy gradient, or the very classic reinforced algorithm, and that's how we come up from starting from the distribution matching, the reverse KR, and then derive this policy gradient algorithm. But in practice, or in the common notation, we are interested more in this kind of conditional policy, where like given the so-called prompts, and you're going to generate the response. And that's the type of policy we are going to optimize, where the prompt is not controlled by the policy itself. Right? It comes from the distribution of a problem people are interested in, or whatever the distribution that you want it to be. That's outside of the control of the policy. And yeah, usually we use the notation of pi to indicate the policy. Okay, so that's the basics of the policy gradient, and we can see that both the policy gradient or the reinforced learning and the supervised learning, they are essentially the same. They are dealing with the so-called alignment. Maybe regarding the alignment terminology of alignment, maybe people will think more about maybe just the supervised learning or the care, the reverse care, the reinforced learning. But basically, they are addressing the same problem, and if you can optimize till the end, like till the KL reaches 0, then they would be equivalent. But in the reality, it's not possible for us to optimize the Q to be exactly the same as the P. Especially for the first case, if you have if you want to make it happen, you need to collect maybe all possible questions that are in the universe and get all possible good or bad responses from the human, and that would just be too much. But there's nothing wrong with optimizing that way. And similarly for reinforcement learning, we would run into a similar problem, but things would be slightly easier. And that's why this second way of optimizing or doing the alignment can be more efficient, or at least easier for human to do. Especially so in this case, for example, for this surprise alignment, surprise fine tuning, sometimes writing a story can be really expensive to collect, and then not to say like writing code or other type of human demonstration. And so the way of doing reinforcement learning is it can be easier to just specify the reward of the piece of text instead of generating the text for the language model to learn. So it's easier to do the judgment than do the creative work. So that's why this approach may be more favorable in many situations. A side note, think about the distillation. Maybe say we have a good large model and we want to teach a small model so that we can put the model on device. Or maybe just we are only interested in like the writing, the coding ability. We don't interested in other ability, though. So we may only need a small model in many situations. So that's the distillation type of work that is also popular. But we can see that from this perspective, like learning doing RLHF or doing the distillation, they are essentially optimizing similar things. Where suppose like P is a teacher model and Q is the student model, then you can either do the like teacher forcing again or use the reinforcement learning to do the distillation. So that is the called like on policy distillation in a recent paper. Here are some results of doing so-called on policy distillation. So compared to so what they do is they do this kind of experiment on the T5 models at a different scale. And the XR model is the teacher, while the small models are the students. And you can see that with the on-policy distillation, usually they can achieve better quality than the supervised fine-tuning. And there can be multiple reasons, but one of the most important reason, in my perspective, might be the fact that for the supervised fine-tuning, it's it is in a mode, so-called mode coverage or mode averaging situation, where say if the student model doesn't have enough power to mimic all the behavior from the teacher, then it would only learn something that is the average of all the mode instead of cover all the modes of the teacher behavior, which may be less ideal. Where for the on policy distillation, basically the student generates the possible response and the teacher using its own likelihood as a reward to justify whether that answer is good or not. So in that case, maybe that's so-called model seeking behavior, where the student may fall into just a one correct answer instead of covering all the correct answers. But maybe that's fine for many situations. So that for a student model which only has like a limited capacity, it may be more desirable. Anyway, that's a side note from the distillation, and just found it to be super aligned connected, and we can derive many things from this distribution matching perspective. Okay, so this is the overall RLHF pipeline. that we start from some kind of language model. Maybe it already knows how to follow the instruction, but not so great yet. And we have some so-called prompt data set, which is basically just a set of questions. They don't have to be labeled. Then you put that into the reinforcement loop. Basically, the language model is going to condition on the prompt you provided and generate the response. Then there will be a separate reward model that can give the reward for the prompt and the response pair. And finally, you do the policy gradient or other type of reinforcement learning algorithms to improve the model. And then the improved model will be responsible for generating the next batch of output and send it to the reward model again. And also for the reward model itself, it also needs to be trained. We'll cover more detail later. But overall, that's the type of pipeline. And so we follow this pipeline to dive deep into also the basics and also the latest advances of reward modeling and also the policy training. Yeah. But feel free to interrupt me. I cannot see the screen, the chat window, but yeah, feel free to let me know if you have any question in the middle or okay. So this is the common RLHF objective, where the first term is something we already just covered, the part where you want to maximize the reward. And essentially that is aligning to, it's also doing the distribution matching to the distribution defined by this reward. The second term is essentially the another care or distribution matching objective that minimize the care between the policy you're going to learn and also here they start from a policy that is trained by the supervised fine-tuning. So the second term is trying to make sure that the policy you're optimizing is not going to run too far away from the reference policy. And we'll cover the reason why we want to do that later. But here is from the very classic, the instruction GPT paper, that as the model size goes and with the PPO, a type of policy gradient algorithm, it can do much better than the supervisor trained baseline and also some pre-trained models. Yeah, so the first part is and I think maybe probably the most critical part is the reward model. It's not that hard to maximize the reward, but it's hard to define a good reward in many cases. So a reward model, in its most common form, is such a model that takes the prompt or the context X, and also the response Y as input, and give you a scalar output. So that's the responsibility of the reward model. So it's plain and simple, but it's hard to train, and it's in many cases it will be tricky to rate the responses from the question or the prompt. So here's one way that we can collect the feedback from human and to train the reward model. So suppose here the prompt is write a short story about a robot and something, and here's one response that looks longer than response 2, maybe contains more detail so that human prefers that over the other one. So you can see it's relatively easy for human to provide this kind of preference instead of generating the response directly. So to leverage this kind of response preference to train the reward model, we can borrow the technique from the learning to rank history. So specifically, what we just talk about is the so-called pairwise learning to rank, where suppose we get a k responses from a single prompt X, then we're gonna enumerate all combinations of any pair of responses among this set of k responses. Then we compute the reward for each prompt and a response pair. And for the given pair, like y w, y win, y lose, we have the human label to tell us like which one is a winner, which one is a loser, and then treat it like a binary classification problem where, like given these two, which one is a winner, and that's basically the learning to rank loss here. So that's the basic idea of using the learning to rank idea to train the reward model in such a way. So you can see that after training, this reward model itself is a shifting environment. Basically, we only care about the differences between two pairs of responses, but we don't care much about like whether this reward is positive or negative. So that's the type of behavior that it would induce. Yeah, so as I just mentioned, this is the delta that actually matters. And since we are doing the learning to rank, there can be many ways. Typically, there are three types of learning to rank. We just talk about the pairwise one. The second one is the pointwise one, where given just like say, think about what we need is the scalar of the question and the response pair. And in some situations, it might be easy for us to come up with the scalar supervision. For example, let's say if this reward is going to characterize whether the generated program is the correct program to the question, then there would only be two outcomes, whether it's correct or not. So it's relatively easy. Or maybe the outcome would just be whether this program compiles or not, or whether it runs or not. So you can specify like a 0 or 1 type of binary reward. But for many other cases, it's hard to give a scalar that just say this is like say the generative story is how good it is to the question. And the last one is list-wise. So it shares some similarity with the pairwise one, but as we just saw, say give key responses from a prompt. Usually for the pairwise loss, you need to either enumerate all pairs or maybe just drop some pairs. But in this case, some list-wise approach can be more efficient in leveraging this. But overall, I think they all contribute to the same goal, that how we can collect the signal from humans so that we can train the reward model and use that reward model to train the language model. And since the reward model itself takes the pair of x and y as input, itself is naturally a language model, or at least a model that share many backbone with the generative autoregressive language model itself. And that's indeed the typical practice of what people do usually. Say, this is the one example of implementation. Say, we take the existing language model so that we can consume the sequence of x and y as the input. And in the end, we only say take the score of the last step, and then especially for this reward model, since we only need a scalar, not a like decoded vocabulary, then we usually like replace the last layer of language model and with a new like regression head. And that can produce the scalar reward and then take the data and train the language model. But this is just one type of implementation, and there can be many other more. But this is the common belief that especially the language model itself is already pre-trained, then hopefully the weights are set to a good distribution, initialize the distribution. Despite that, we are not going to do the language generation task. But one problem is with this reward hacking. Let me see how can I. So this is a game, a very classical game called QWOP. So basically, you have 4 actions that the goal is, as you can see, that the reward is how long you can control this human to run, and the longer, the higher reward it is. But clearly, the language, sorry, in this case, it's not a language model. Clearly, this model didn't know how to properly run, just to do this kind of weird behavior that maximize the reward. So this is the type of reward hacking, where that it achieves the high reward. You can see that it can keep running and keep moving and keep accumulating reward, but didn't learn the desired behavior that we want. So that's the reward hacking thing. And similarly, reward hacking is the issue for the language model learning as well. For example, here is some typical reward hacking behavior, but there could be many more. So, for example, first example is say that you use the quite many emojis in the response. Maybe people like it, but sometimes I feel it's annoying. And also sometimes it would generate repetitive and nonsense responses. For example, like it tries to pretend it is thinking, but what it generates doesn't quite make sense, or just repeating what is the question is. And a third case is like a formatting issue. Like say, sometimes we don't need these many headers or format that doesn't contribute to how fun the joke is. So that these are the very common behavior of reward hacking. So that's a very challenging problem in the RLHF, and I don't think that this problem is solved. So there are, but before solving this problem, we need to learn like how this could happen. Firstly, I think for the human preference, we would sometimes introduce our bias into the preference. For example, in this case, let's say enter the words that satisfy the given condition, and both of them should give us the correct answer. But it's just like the second one, the on the right hand side, is more concise, while the left hand side one is more formatted, and that's why maybe human just prefer that. But since like when we train the reward model, we only know that this left one is preferable than the right one. We don't know that both of them are good, and they just a formatting issue. So implicitly, we are adding the formatting bias into it. And similarly, the emoji bias, where in this case, like the left one and right one, they are also basically the same, but left one maybe having some emoji that getting more preferable than the right one. So that's that's a big issue. But on the other hand, we maybe the human we basically have this kind of bias towards like what is the maybe more formatted than the other. So this is the ranking collected from the LMSys arena. On the left hand side is the overall ranking, and we can see the GPT-4 mini here. Let me see if I can bring up the laser. So GPT-4 mini is doing really great, and even better than the Cloud Sonnet. But if we apply the so-called style control thing, the hope is like remove the contribution from the styling factor, then we can see that the GPT-4 mini is not here, at least not in the top 10 yet. So yeah, that's a huge difference. But nothing wrong with GPT-4 mini, and nothing wrong with preference over style. It's just like maybe sometimes we don't want we want something that is actually intelligent, not necessarily like exploiting human preference in that way. So that's the one reason. And another reason is as the language model itself is a neural network, we all know that the neural network may be prone to the adversarial attack. So this is a very classical attack for the GPT, where you say that you pretend that this is a so-called grammar attack, where you ask the GPT to act as the grammar, and they will just follow whatever instruction you would say. So for the reinforcement learning, it's similar that basically you're trying to attack the reward model in such a way that you maybe optimizing the reward, but getting high reward doesn't necessarily mean you get a good response. It maybe sometimes it just means that you get a, say, vulnerability of the reward model. So as we can visualize in this way, say the x-axis is the care, the distance between the current policy and the reference policy, maybe the policy after supervised fine-tuning, and the y-axis the reward. As we can see, as the training goes, you get further and further from the reference policy, and your reward gets higher and higher. But suppose there will be true reward, and sometimes you will see the reward will get plateaus after several iterations, or even getting decreased. So that's the type of behavior we want to avoid. So that's why going back to the previous slides, that when we talk about the objective of RLHF, we want it to be close to the reference policy, so that we don't exploit too much from the reward model, because usually the reward model is trained on the preference pairs that where the preferences are the responses from the pair are generated by the reference policy or the policy at the beginning. So we don't want to stay like getting too far away from there, because the reward model hasn't seen much, or if we stay too far away from there, that will be an out of distribution sample for the reward model. And another approach is like we can have another reward model just to monitor. But we need to make sure that these two reward models are different. And thirdly, we can do some ensemble for the reward model to mitigate this issue as well. For example, this warm paper, they simply train multiple reward model and do the weight average of them. And that seems to be super helpful. Another one, which may be more expensive, is say we train multiple reward models, and during RLHF, we get the reward from each reward model, and get the so-called lower confidence bound from this many reward ensembles, and that would give us a more conservative reward and somehow can mitigate the reward hacking problem. But overall, still, they all have their own issue, and the reward hacking is indeed, I would say, an open problem in this field. Yeah. So since the reward model itself has many disadvantages, we can think about other type of reward model, or say just a reward, not necessarily having a model behind it. For example, in this case, suppose we ask the language model to generate some fancy program that in the end prints the hello world, then we can easily check if the program is correct or not by taking a look at the output and see if it equals to the hello world or not. So that's the type of reward that we can get from executing the code. And usually that will be preferable, because code execution is faithful to the code, and a unit test, despite the coverage of a unit test, as long as we have like good set of diverse test cases. We hope that it would be able to capture how good the generative program is, and that would be a very faithful reward. But the problem is not all the prompts have this type of reward, and also running the code sometimes can be annoying. You need to bring up the like the virtual environment, and also having other things set up, the sandbox set up. But overall, it has been used in many like open source code language models. And the second case is the so-called generative reward model. So far we talk about the reward model as a model that only produces the scalar in the end, just like this line. But what if the reward model itself can do the chain of thought thinking? Then maybe it would, after like, if the reward model itself can do the reasoning, then hopefully it can capture more on the outcome from the response from the language model. And in this particular case, say that the reward model itself does the thing step by step or verify step by step. And in the end, if we sample multiple times from this chain of thought and do the majority voting, then we can get a more precise reward from this so-called generative reward model. But in this case, we don't expect much about how calibrated the scalar would be. So usually, to use the generative reward model, we can either put it in a preference pair, say give a question and two responses to this generative reward model, and the generative reward model would think step by step and tell us which response is better, and that will give us more robust reward. Instead of we can also maybe have the generative language reward model to generate the scalar, but that would be less calibrated. And one more thing is that people usually think or hypothesize that the success behind the O1 model from OpenAI might be they have more detailed reward in the intermediate steps. So far we the type of reward we have is say on the entire response level, but in many situations, if we generate a long response, maybe the response itself contains the chain of thoughts, like step-by-step reasoning. So not all of them are correct, and I know not all of them are wrong. So this process reward model in this very early paper, what they do is have human to rate the correctness of each step, so that they can train the reward model, also the process reward model that provided the supervision for intermediate steps, and that would give us a much denser reward. But the problem is you need a extra human effort to label the correctness of intermediate step, and that definitely would cost more. So there can be an alternative approach. So this is from another paper where suppose we can verify the correctness of the generated answer in the end, then we can actually build back to the intermediate steps. Say, for example, we generated these many solutions, and the solution here that's incorrect, but maybe the intermediate step we go through k steps, then we can somehow calculate the probability of generating the correct answer from the intermediate step. To do this, what we can do is at a certain step we can do Monte Carlo rollout of this current policy and see whether in the end you get a correct answer or not. And let's try this k times and see how often do we get the correct answer, and that would be the success rate starting from that intermediate step. So probably if you start from a fourth, like a wrong step, then you would never get a correct answer, then that would tell the quality of the intermediate steps. So that's, but how to reduce the sample complexity of this Monte Carlo estimation, that's another research topic that is trending in this field. Yeah, finally, the reward bench is another benchmark that I think it's pretty important. If we have a good reward model, it can kill climate, but as we can see that sometimes, or in most cases, the language model, the generative model itself, is not as good as a dedicated reward model in this benchmark, especially like for the latest GPT-4 model. The rankings not good on this benchmark. So how to mitigate the gap between a model as the generator or a model as the judger? I think that's another interesting question to explore further. Yeah, when we talk about reward, there can be multiple dimensions as well. We not only optimize the helpfulness, we also need to take care of the safety of the response. And also we want to make the sometimes make it concise so that we don't annoy people, but sometimes we also need to show the empathy or the like creativity. So there are too many dimensions to think about. So in the reinforced learning, like a policy grading framework, we cannot easily take these multiple reward together. A commonly used method is to add them together so that we can form a scalar reward in the end. But we may have different preference or the weights on different reward, and maybe we emphasize safety more, so that in the end the trained reward model, the trained policy model would put more weights on the safety, but maybe less on the helpfulness. Say, but in this case, it's really hard to compare the model with another model. Say model A is more safe but less helpful, but model B is less safe but more helpful. So from the reinforcement learning perspective, or we cannot really say that one is better than the other, because we only see the scalar reward that is the weighted average of all of them. And that's why it's a hard problem, not only the technically, but also starting from the definition. Usually, there's nothing to blame if you achieve the so-called Pareto frontier, where it means there's no other model that can be better than this model on every single dimension. As long as there's no such other alternative models, then you're good, you're on the frontier. And from the multiple objective optimization perspective, you're done. But the problem is you can easily hack this kind of parental frontier, like say, just optimize the safety. And no one can be safer than me. But maybe I just say nothing for all the questions, and that will be the safest. But the parental frontier doesn't define a good model in this case, obviously. So more of a hard question is how to define a good behavior. And that's usually the it's very vague that what type of behavior we should align the model to. And that's why I say at the beginning, the reward model itself is maybe the most critical part in the entire RLHF pipeline. Yeah, before I jump into the next part, any question or any comments on the reward model? If not, I'll just proceed with the policy optimization part.
Hanjun, I think there are a few questions in the chat. Do you want me to read it for you?
Yeah, that would be great.
Okay, so the first question is from Soshizmit. Sorry if I mispronounce your question. So the first question is actually quite a while back, asking about the KL diversions.
Yeah.
in the beginning. So if the divergence of P with respect to Q is easier to compute, then why exactly are we considering taking the reverse direction? More so when the latter is harder to compute, what do we gain from using the reverse direction?
Yeah, that's a very great question. And I think the answer is yes, the first term is easier to compute than the second term if we have the samples from P. But the problem is it's easier to optimize once you have the data, but it's hard to get the data itself. As we show in this slide, like say, if you want to train the language model to write good code, if you have like a let's say 10,000 experts sitting there to write the code for you and collect the example and then teach the language model, then for the optimization perspective it's easy, but it's so hard to have 10,000 experts sitting there to write code for you. So that's why we hope to do the other direction where getting data is easier but optimization is harder. Yeah, I hope that answers your question.
Perfect.
Maybe I can take another one. If
Yeah,
there's
there are a few others. Let me go to one more, which is more recent. Whether reward models or LLM think, wait one sec. Whether reward models or LLMs think or not is not up in the air. Even if they are considered stochastic parrots, the generation is conditional in nature. Using COT or multi-step generative steps, at least, we can try to move to potentially a better space in the generative space, i.e. if initially without multi-step reasoning, model was generating from argmax token, now it is generating from, argmax token, P token given context. Now it is generating argmax token of P, a probability of token given context and also intermediate step output, right? I think that makes sense.
I don't know if I'm getting the question, but my reaction to the, I suppose you're asking about the, like the, say the discriminative RM where it just generates the reward versus the second case where you have more uncertainty in the middle. And one thing that maybe I need to correct is it's not doing it's argmax doing the, but you need to integrate over the intermediate step. That's like a summation, not the argmax. So the intermediate COT is more like the latent variable that you want to marginalize out. So that would give hopefully more robustness, and maybe that's why maybe with the COT and with this paper called self-consistency, that can together contribute to more robust reward than just outputting the single scalar. Yeah, but maybe we can dive deeper into that later. Yeah, I will move on and we can have time for questions later. Yeah. Sure. Second part is about some, again, these are more reinforced learning focused. So depends on the interest. Maybe I think people can do it more offline, but I will cover some high level topics and I wouldn't dive too much into the equations or derivations here. So the first practical issue is we can optimize in such a way, but it'll take a long time to converge. Main issues of this so-called variance of the gradient estimation. So a common practice is to subtract the reward by a so-called baseline, where the baseline would be so-called value function that can calibrate the maybe the how good your current response compared to the average response in your current distribution, or it can even be as constant. Surprisingly, as long as you can find a good constant for that. The high level idea, I wouldn't dive too much into the mathematical thing, but the high level intuition is say if the reward you get is always like say positive, then for the policy gradient thing, the direction they are almost the same, and it's hard for you to like think about how to maybe maximize or minimize certain likelihood of generating response. But if you subtract the baseline here, then sometimes you get a positive reward, sometimes you get a negative reward. And a positive reward would encourage you to put more weights on this response, while negative reward would say discourage you generating that. So that's more obvious way of doing the contrastive thing. And we later will cover the DPO, and that would exploiting this property more directly. And the second practical issue is how to attribute the reward in the middle. We just talk about the PRM, where we have the process reward that is like directly trained to provide the intermediate step reward. But suppose we only have the reward in the end, how we can attribute the contribution from the intermediate steps. This is also a classic topic, and starting from the generalized advantages mentioned, this is the core component in one of the core component in the famous PPO algorithm. Again, I wouldn't dive too much into this, but more of like sharing some pointers that that if you're more interested in how to make a reinforcement learning itself be efficient, these are the dimensions you need to consider. Finally, we talk a lot about, say, given the question, you generate response and get reward, and then you are done. And that's more like a single step reinforcement learning. So how we can do this properly for multi-turn dialogue, especially in the situation where we have the response from the user, or maybe from his external feedback from the compiler, or execution feedback from whatever virtual machine, then how we can take that together with the previous response, the previous question at the beginning itself as the new context, and provide a new response in the second turn. So this multi-step reinforcement learning is also critical, but in order to do that, you also need to have a good kind of a simulator or environment simulator to interact with the model itself. And this brings the challenge for both the simulator and also infra side, how to make this training efficient. So here's a recent paper thinking about how to teach the model to correct the previous response by simulating the feedback. But this is just one type of work, and there can be more general feedback or simulated out there. And that's, I think, another important next step for language model to learn. Yeah, so here just to provide some concrete outcome of the real RLHF that you can expect. So here we take a very simple experiment. This is an experiment from the instructor GPT, where it's called the TLDR. The goal is to give them paragraph. Let's summarize that, and that's so simple. Input is paragraph, output is a summary. And so here is the experiment setup we did. We take open source T5XXL model, and we first do supervised training using the provided dataset for 20 steps, and then do the training step of reinforced learning. So we want to see how much we can improve from the supervised fine-tuning. And just give you a rough idea that how long does it take and how much compute it consumes. But definitely for the infra side, you can always optimize it, but that's roughly the number of TPU or equivalently the GPU and the amount of time you would expect to take to train this scale model at these many steps. And here are some outcome. So this is the first is we take a recent Reddit post. This is still considered as in distribution, despite that the model has never seen this post. For the pre-trained language model, of course, it doesn't even know how to follow the instruction. And for the supervised fine-tuned model, it can get something out of it, but didn't capture all the detail. I think this post is talking about some old guitar and thing, but completely missed that. For the pre-trained flying model, it can capture some, but not all the details. So surprisingly, after RLHF, it can capture all the details and being concise at the same time. Here's another interesting example where we do the news summary. The reason why it is interesting is we only train the language model on the Reddit summarization task, and we help it to summarize the post from this or CBS sport news. So that's kind of interesting that it can also generalize to other distribution of the inputs. And finally, like some financial earning reports, it can also do much better than the alternative, where the super fine-tuned model sometimes wouldn't capture relevant details, and FLAM model would even give us some false claims. And in this case, the RLHF model would give us much better results in this case. So we can already see in this toy example that after the some training of the RLHF, it can give us the outcome that is kind of beyond our expectation, because the dataset, the Reddit dataset, is really noisy, and even for the preference pair is not of a good quality, but the reinforcement learning can bring us much more than the data itself provided. Yeah, so far we talked a lot about the RLHF. Maybe for the rest of the time, we cover some other alternative to the policy grid. Despite that, still the policy grid is most effective way, or at least like regarding the quality wise, it still give us the best quality most of the time. But it is expensive because sampling during training we need to do the so-called on-policy sample. And the sampling can be expensive because it is an auto-regressive model that introduces the serial dependency. You can only generate this token before generating the next token. And unlike during training, you can feed all the tokens together, do a one-fold pass, and that will give you the probability or the likelihood at each token position. So that's the one major bottleneck. And especially the longer the sequence, the slower it will be to sample, because of the transformer architecture. And also during RLHF training, you need to take care of so many models, like a policy model that you're going to train, the reward model that give you reward, sometimes all kinds of fancy reward as well, and the reference model that you want to calculate the care against, so that you don't run too far away from the beginning. And lastly, or optionally, you have a value function to reduce the variance, as we covered earlier. So many things and so complicated. But that's why the DPO, the so-called direct preference optimization, can be popular. All they need is just the preference pairs, not even the prompts, no, something else. And it can learn from this preference pair to, and it only needs to train a single model, the policy model. It doesn't need to train the reward model. And some recent work can also show that you can even avoid the need for the reference model. But let's start from the classic DPO. So recap, the RLHF objective is like this. And I will directly copy paste the conclusion here, and you can derive it yourself. It's not hard to do it. So the optimal solution from this objective should follow this kind of exponential form of the distribution, where the beta is the coefficient for the KR regularization, and the R is the reward model, and Z is the normalization constant that later on we can show that it doesn't matter. So basically, it's like the optimal solution is the composition of reference policy and the policy kind of distribution defined by the reward model. So from this equation, we do some just reorganization. We can get the relation between the reward model and the policy. And then we can see it follows such kind of correlation. So suppose like we have the preference pair, then when we train the so-called reward model, we do the so-called binary model. Basically, it's like a binary classification, where if we subtract the reward from between the pair of y1, y2 generated by generated by a prompt, then all we need to take care is that this delta difference between these two log ratio, and this log z partition function is completely cancelled out, and that's why we can simply train this binary classification. Then we can hopefully to align the policy that we are going to train. And DPO can be very powerful despite it's super simple. The left figure is from the DPO paper itself. You can see that this top curve, maybe this curve itself is a bit problematic. Maybe you need to pay more effort to get DPO working. But that also says that it's not easy to make the PPO working, but it's so easy to make the DPO work to some extent. And secondly, even the latest Llama 3.1, they use synthetic data to train the model, and also they mentioned that they use the rejected sampling and the direct DPO to optimize this model. So it can be super powerful. It can be super useful. And also, it opened up another possibility of optimization. For example, this is a work from the Meta as well. They're envisioning a self-improvement language model where the data is generated by the language model and it can improve by itself. So the idea is to get the set of prompts, generate responses from the prompts, and collect the preference pairs. So collect the pairs of responses from the generated ones, and use the language model itself, like the generative reward model, to label given each pair which one is better, which one is worse. And given the labeled pair, you can just feed that into DPO, and that can give you a new policy, and you can continue this loop. It may have its own limitation, and maybe it would plateau at some point. But just to say that the simplicity of DPO would open up kind of a new opportunity for optimization. But DPO can be problematic. In this toy example, suppose we only have 3 actions we can take, and the reference policy give us this, and we only observe the preference between Y1 and Y2. So Y1 is more preferable than Y2. So ideally, we should get a policy like this. So we put all the mass to the Y1, but for DPO, it would derive a policy that put much weight on Y3, where Y3 is not observed during training. So I really like this toy example. It's from the recent IPCML paper. But the reason is that the solution space of a PPO is a proper subset of the solution space of DPO, which means that the DPO can develop a biased distribution favoring unseen responses, and that could be problematic for the quality. So natural idea is to say, can we make the DPO online? Let's say in this figure, we generate a response from language model and have a separate annotator, maybe another reward model to label which one is better, which one is worse, and feed the fresh pair into the DPO objective and train it. That would work if we have a good labeler on the fly. Suppose, let's say, we use the same reward model as the RLHF. It can do something that is better than offline DPO to some extent. This is from the on-policy DPO, online DPO paper. But the problem is it didn't count the exploration bit into it. So this is a more of a theoretical RL, where you are not going to only optimize the current reward, but I also want to explore the region where you haven't touched before. And maybe in that region, you would have higher chance to hit higher reward, but you will definitely pay the cost of missing some opportunity. So this is a classic problem in the regret minimization, where So here is just a simple example. So say if you sell your stock too early, then you miss the chance of winning that portion. But who knows the stock would go up or go down. So under the optimal situation, like compared to optimal policy, what's your gap here? That's the regret. And so in our recent paper, we study this online fixes for DPO, where in addition to the DPO loss, we add another term that encourages the exploration for the DPO policy. And it's as simple as just adding another likelihood that like unlikelihood saying that whatever sample responses you generated from the policy, you should discourage the likelihood of generating it further, so that you can have a chance to explore further. And we can provably show that this one has the same regret as online RHF. And similarly for the offline case, when we want to be more conservative, all we need to do is simply flip the sign of from the plus to minus, so that we can be conservative to the offline samples. And the last one I'm going to share is the so-called best-of-N sample in the distillation. So that's another type of, and also a recent hot topic in this field. And I will first explain what is the best-of-N. So suppose you have a trained policy, the language model, and you generate, let's say, M responses. And suppose you have a reward model as well, then you can use the reward model to calculate which one gets the highest reward, and just put that as the output. So zooming out a little bit, if we treat this entire procedure as your policy, let's denote it as a pi best-of-N policy, then from like treat it as a black box, you just put the prompt as input and the generated response. So that is self-defined kind of policy. So that's the so-called best-of-N policy. And it has some nice property. For example, a recent interesting topic is about how to spend more compute during test time so that we can improve the quality further. The best-of-N is the one type of approach. So this figure is taken from the recent paper called a language model monkey something, where you generate many candidate solutions. And suppose you have a good verifier. Let's just pick one that maybe the unit test or other reward model even, and then get the response from it, and you can hopefully improve from just a sample from a single response. And here's the so-called scaling curve of best-of-N in their paper. As we can see that compared to a single attempt, like the red curve here, if we get more and more like a 10 responses or 100 responses, as long as we have a good verifier, then we can further scale up the performance to be something like even starting from a model that is not as good as GPT-4o, one can improve the performance further. And this is the theoretical work telling you that what is the best-of-N is doing, and it shows that best-of-N is trying to do this win rate optimal policy, where suppose like you given the care distance, what's the best policy you can achieve under this reward pairwise preference. Then this paper, the conclusion is that with large enough value of N, like a large enough number of samples, the best-of-N policy is optimal. So, which means you can literally don't do anything like a RLHF. Suppose you have a reward model already, you have the starting policy, then let's just don't train the policy. Let's just do best-of-N policy sample, and when N is large enough, you can maybe get a better and better model. That's good, but best-of-N takes time. You need to sample N times, and we all know that sampling, like a generation, is even more compute expensive than training fitting the single sequence. So a natural idea is suppose we have the best-of-N policy, then can we do the distribution alignment of another policy pi such that we get close to the best-of-N directly? And the natural idea is, again, do the forward care. Say we sample the policy as the responses from the best-of-N and just feed that as the supervised example to your policy. But following our understanding so far, doing that in the other direction can be more efficient, and the quality-wise can even be better than the first one. So the recent work focuses a lot on how to do the best-of-N distillation in the reverse KR formulation. So starting from the reverse care, we all know we skip the derivation. We already know that the conclusion of the policy gradient of optimizing that is suppose we have the so-called reward, then we can do the policy gradient. In that case, the reward is basically characterizing the likelihood of a given response y under the prompt given the pair of x and y, the likelihood of generating y given x under the policy of best-of-N. And this is not something that is easy to compute, because best-of-N, you implicitly have a ranking term there. So to calculate the likelihood of generating something, you need to characterize the likelihood of this solution being better than all other solution generated in this batch. So here is like a kind of cumulative density type of calibration that need to take into account. So it's not easy to compute. And some recent paper is talking about how we can make this easier to compute. And as long as we can compute this kind of, or approximate the likelihood of generating y under pi of best-of-N, then we can do the best-of-N distillation in a more efficient way. Yeah, so far, just give a brief summary of what we have talked about today. We start from the distribution matching perspective, and think about all kinds of distribution matching algorithms. And specifically, we talk a lot on the policy gradient, and that's the most popular one that has been used to train a lot of great language model. And we also talk about this limitation on especially the cost, and also the difficulty on getting it right. So the alternative solution would be much easier to optimize, or at least to start with, like a direct preference optimization above best-of-N sampling and the distillation. They would have like a higher, or like they would make things easier to work, but the headroom may not be as high as the policy gradient. But in most of the situation, we are suffering from getting things done right. And we talk a lot about the difficulty, and especially for the reward modeling. That's the most critical part, and how to get the good reward and how to avoid the reward hacking. And also, optimization itself is not an easy problem, especially when you have like a large language model, when the scale goes large, and you would definitely have like how to think about reduce the variance, and also how to attribute the reward properly. That's the thing, the optimization thing, not only for the language model, but it's a long-standing problem for reinforcement learning itself. And yeah, so a lot of to consider, and like making it practical, making the cost efficient. Costing is not only about the computer cost, but also the cost to get the human label, and also the need to think about the quality of the human label as well. So it's a complicated problem, but people are making great progress so far. And this only capture a subset of the progress, and I believe more will come, and the language model will be better and better with this kind of approach going forward. Yeah, so that's roughly what we have today. And yeah, I'm happy to take more questions if we have time.
Mayur, I think you're muted.
Who is muted? Me. Okay, we do have some time for questions. Ziang, would you like to? Well, how about from folks here? Does anyone have any questions? Or we can give folks from the chat a chance first. Ziang, would you like to coordinate this?
Yeah, I think we should prefer the offline questions if there are some, but if not,
They'll come. I think we
yeah,
should just, there are many in the chat, so it would be nice to go over them.
I think we already went over
I
a
see.
few. There is one question. Oh, I guess there are many people in the chat just talking and then they answer the questions. For example, one person asked, what is the difference between DPO and PPO? And then there's already some answers. I don't think we need to go over that. One question is, how do we define the loss function for list-wise reward model training?
Yeah, that's a good question. That would I would attribute more on the learning to rank literature. So for example, for this one, I think I can still, people can still see my screen, right? So I would suggest reading from this paper, so-called From Pairwise Approach to Listwise Approach. But the TLDR is one way to do that is maybe just to think about what is the best one here, and treat this as a multi-class classification instead of binary class classification. So we put all of this together and we put the rank 1 here, and that's like it's like an choose one type of classification loss, and that's one way to do it. Another way is we can put some discounted weights on different responses. For example, we think the top one should get the 0.5, second one should get the 0.2, etc. Then we naturally have a distribution of these responses, and that's become another kind of distribution matching loss. And you can literally use like cross entropy to optimize the list-wise loss, and that can be more at least compute efficient than doing all pair of pairwise loss. But there's huge huge literature on the learning to rank, and if you're interested, you can definitely learn more.
Yeah, thanks so much.
Another interesting one is, do you think it's more promising to improve faithful chain of thought via inference time computation or through RL training?
That's a great question. I don't think they are conflicting with each other. I think the reason why the language model is able to use the chain of thoughts and generate the chain of thought in a proactive way, and the more training results would result in more higher quality. I think that's thanks to the training time reinforcement, and I think these two are coupled together. But I think the interesting question is more like how we can induce such behavior during training, especially like suppose you just enlarge the sampling size or the number of steps during training, and if you don't have a good reward, it's just enlarge the space of reward hacking, and the language model would be super genius on coming up all kinds of crazy hacking patterns that would achieve a higher reward than you can imagine. And I think the difficult question is how to make that make a proper reward, and especially the reward that are not only coming at the end but also attributing to the middle. Yeah.
Ziang, there's a repaste of a question. Can you read that one out?
I think before that, there's one more. Do we still have time?
Yes, we have
Okay, so
2 more minutes.
yeah, let me just read the prior question. How to diversify the outputs when doing Best-of-N besides temperature and prompt?
Oh, yeah, that's a good question. So if you say that, I think the one thing is the policy itself needs to be diverse. Otherwise, if you sample n responses and you don't get the difference, then doing best of n is not give you any better than the policy itself. So the maybe we need some high temperature for the pi itself. Let me bring up the page. We need some high temperature for the pi itself. And yeah, regarding the diversity, I think here the after you come up with the n responses, if you are aware that this pi of best of n itself is going to run many times, then you need to take account. I think you can make some progress on the reward here. Maybe like taking into account saying that you have generated something in the previous trial, then this time condition on maybe the similarity between and the reward itself, you want to do some trade-off here, and you can have many different ways to take into account the diversity. Yeah.
Okay, perfect. So another question is about comparing supervised fine-tuning and RLHF. So basically, the question is about if we have, early in the presentation, you mentioned that supervised fine-tuning might not catch as many details as RLHF, but what if in an ideal world, we can afford to gain enough very nice supervised fine-tuning data for training? Would SFT be sufficient?
I think the answer is yes. If you in the ideal world, if you can get all the responses, because like suppose our generation is limited. I mean, the context length is limited by say 1 million, and there would only be combinatorially many but finite number of responses. Then it's possible to enumerate all of them and see how you can fit that distribution. Yes, that's possible. But the question is more like, if you have that capability of generating that many responses, can you use that capability to do something else? And maybe that can be more efficient. I think there's always a trade-off. So from mathematical perspective, there's nothing wrong with these two losses. And you can also use like so-called Jeffrey divergence to add these two together to make it a symmetry, this divergence. But again, you cannot think from the ideal world perspective. You need to think about given the same amount of compute, what is the best way of using it? What best way of spending your budget? And that's why like we have this trade-off.
Okay.
Very nice. I think at this point we need to stop. We are over time. Let's thank Hanjun once again.
Thanks, everyone, and all great questions. And if you want to have more discussion, feel free to reach out and send me email. And also, if you have any research interest questions or like a hypothesis, I'm also happy to discuss further. Yeah.
Yes,
Thanks
and I
again.
will make the slides and the recording available to everyone. Okay.
Sure. Yeah, I will share the slides with you afterwards.
Thank you very much, Hanjun.
Thank
Bye.
you. Thank you.
Thank you.